So 2025 has been named the year of agents, and we're about halfway through, and it's turning out to be the case. Every single day there are new models released, more and more intelligent and more capable of handling agentic tasks. And so the landscape is shifting from less of a bottleneck of intelligence to more of a bottleneck of orchestration and handling these multi-agentic systems. So as most of you know, multi-agentic systems are sort of the hype at the moment, and they are sort of the future of LLM applications as they help you both scale performance as well as complexity and intensity of the tasks that you solve. So in this video, what I thought I'd do is walk through this amazing blog post by Anthropic called How We Built Our Multi-Agent Research System, which goes into the findings and learnings from their production grade research-oriented agentic system. And if you guys are new to the channel, my name is Nipuna. I'm an AI engineer that builds solutions using generative AI. And in this channel, I just basically document my learnings and also the things that I build. So if you like this video, please leave a like and let's get right into it. Also, huge credit to Anthropic for releasing these amazing blog posts. I will leave the link down below if you want to check that out as well. So let's first start off by defining what exactly is a multi-agent system. So essentially what Anthropic are saying here is that a multi-agent system consists of multiple agents, LLMs, autonomously using tools in a loop, working together. And basically the research agent that they're going to be talking about in this article here is one that plans a research process and then uses tools to create parallel agents that basically search for that information. And this whole thing is done simultaneously to, at the end of the day, give you a report, sort of like deep research in OpenAI. So before we get into the details, let's talk about why it's beneficial to use a multi-agent in this scenario as opposed to a single agent. So Anthropic says basically research work involves open-ended problems where it's very difficult to predict sort of the step-by-step path that anyone would take while doing that essentially research. This is a scenario where you have a problem where it's quite open. It's not really a step-by-step workflow that you can hard code. You sort of need to make decisions on the fly, and this is essentially where agents shine, and especially multiple agents. So whenever you're thinking about doing a use case, always figure out, is this something that where like an agentic system would shine, or am I really better off like sort of making this a workflow? Because you're, as you'll see in this article, you're signing yourself up for a lot more complexity if you did decide to go the agentic route. So in this scenario, the model must operate autonomously and make many turns. And essentially the sub-agents are basically distilling the information they find all the way up to a lead orchestration agent. So this idea of using sub-agents to essentially do sub-tasks or sub-processes and then compress that information up to a lead research agent is a common agentic design pattern that many people have used. So if you imagine a linear one-shot pipeline with a single research agent, and we gave it the task, research the best locations to visit in Canada, what it would have to do is essentially make multiple individual tool calls, maybe parallelly, to basically research, okay, what are the best locations in Canada? And then maybe once it comes up with that list, okay, what is the places to visit in Alberta? What are the places to visit in Vancouver? And so on and so forth. So it would have to do multiple tool calls here, whether it had documents or web search, it would do all of that in a single chat history. Now you can see how that system would essentially differ from this one, where basically we can send that same research query, except now we have an orchestrator who decides where to go and what to do. What they will first do is call a planner to figure out basically how will I actually research how to figure out the best locations to visit. And the planner will respond and give the orchestrator a plan. Okay, like research, this topic. And then what it can do is instead of calling those tools individually by itself, it can hand that task over to an individual agent that will basically have its own chat history or its own memory, perform that search, go a little bit deeper, summarize those results, bring that up, and then essentially bring back that information to the lead agent. So this approach both increases performance as well as the complexity of tasks that you can do, because now you have not just one brain, but sort of multiple brains working together in parallel. And that's really the power of multi-agentic systems when you come to these open-ended tasks, is that you can sort of scale horizontally as much as you want, as much compute as you want. So you're both scaling performance and complexity, but obviously it comes with its drawbacks as well. So getting back to the article here, you can see that Anthropic are saying multi-agent systems work mainly because they help spend enough tokens to solve the problem. And in their analysis, what they found is that these architectures burn through tokens very fast, and pretty much a single agent might use 4 times more than a chat interaction, whereas a multi-agent system will use 15 times more than chat. So you can think of these systems as very expensive, but the payoff is that if the task that you're doing, has some sort of revenue benefit, that value and that time spent is usually almost a positive ROI as opposed to getting a human to do it. So here's the high-level architecture for their multi-agent research system. You can see, just like the diagram I drew, we have a lead orchestrator agent who essentially has some tools and its own memory. And basically it will be spawning these search research agents that essentially go off, do their own loop, and then come back with the information where the lead orchestrator will decide, okay, do we search more? Do we go further? Do we just synthesize a report? And so on. And you can see over on the side, related to this use case, there's a separate agent which is directly responsible for checking citation. So here we have the sequence diagram. And if you start from the left-hand side here, you can see the user will send its query. And you can see here we have the system with 3 different agents, actually 4, including this one. But we have a lead researcher. You can think of this as the orchestrator or sort of the main agent that is sort of driving this process. And then we have 2 sub-agents that basically perform the research. So once a user sends a query, we create a lead researcher agent who then first, what it does is it figures out, okay, how do I actually research this topic? And this is an important point that you'll see later in the article, is that generating a plan first in any multi-agent system is probably a good idea before you start immediately handing over to sub-agents. So once it has a plan, it's going to go ahead and persist that plan in memory. And so this could be some sort of database, or maybe it's some sort of cache, but essentially it's going to persist that plan. And the reason for this is that Anthropic mentioned it right here. Once a context window exceeds, because, the agents are researching things, it's likely a large amount of context. You want to persist that plan and not just lose it as you truncate the chat. So once it's saved that plan, it's essentially then parallelly creating 2 different sub-agents. So these 2 guys here, to then go ahead and research individual topics. So, if our research query was what are the best locations to visit in Canada, maybe sub-agent 1 would research Vancouver and sub-agent 2 would research Alberta. And essentially they both go off and do their own tool use and their own sort of search. And these are likely happening inside isolated chat history. So each one of these will be a separate context that is sort of hidden from the lead researcher. So essentially the lead researcher isn't seeing all the different tool calls that are being made here to essentially keep the context clean. So this is a very common pattern that you'll see across these systems, that each agent will have their own memory, and that memory won't necessarily be shared with the orchestration agent. So once they've gone off and done that research, they will come back with a complete. And basically the lead researcher then synthesizes that information and then determines, okay, do I exit or do I continue? And likely this loop will run for X number of iterations, or I'm sure Anthropic has set a limit in their prompt or a manual limit as well. And then once that's done, they will complete the task. The citation agent will essentially make sure that the citations are valid, and they will persist the results before returning that back to the user. So you can see sort of how the actual agentic system works, and the different aspects from planning, saving that plan, to how each individual sub-agent gets called parallelly, and then how all that information gets synthesized at the very end. Actually, one of the other interesting things that is written here is basically that the agents are using interleaved thinking, which is essentially where after they make a tool call, they will basically run a sort of thinking stream to determine, okay, did I find the results that I want? And this process, Anthropic says, basically helps the agents sort of stay on track and determine whether more research is needed. So it's sort of using a reasoning model as it's doing the tool calls and getting those results. If you have the compute and the tokens to spend on that, it makes sense to do. So in this section, basically, they highlight a bunch of different prompt engineering techniques that are generally useful for not just research agents, but essentially agentic systems as a whole. So tip number 1 here is to think just like your agents. Now, how do you practically actually do that? So what they did was they essentially did a lot of simulations in their console. And they essentially watched the agents work step by step. And that told them, okay, these are the potential failure modes that the agents might run into. So one of the examples they gave here is that the agent already had sufficient results, and they were basically just continuing to search more and more deeper things when they really didn't need to. So that then tells them, okay, in our prompt, we need to instruct the agent to determine if you have enough results and then stop the process to avoid going further. You only really find this out by trial and error and testing. So I think the broad tip to take away here is to set up some sort of dev environment or a notebook that you can just test each individual agentic component separately. And what you'll find a lot of the time is that Gemini might do something completely different from OpenAI's GPT 4.1 when they're given the same tasks. So each model will have sort of their own way of calling tools, their own way of making decisions, and that's up to you to decide on which one best fits your use case. So tip number 2 they have here is to teach the orchestrator how to delegate. So in their system, they essentially have that lead agent that then spawns multiple sub-agents and essentially waits for that waits for them to come back before determining, do we go and spawn more agents, or do we, bring back the research to the user. And so here they basically are describing that you actually need to figure out how to tell the orchestrator at the very top to do their job. Without detailed task descriptions, the agents duplicate work, leave gaps, or fail to find necessary information. And what they found was that giving simple short instructions like research semiconductor shortage was vague and not really helpful to the sub-agent. So they tested this in their dev environment. And then what they saw is that if you just give the planner or the orchestrator, like, here's a research query, hand this off to some sub-agents, it will probably duplicate the work, and it will probably not really result in an efficient search. So the tip there is essentially to just build very specific handover rules and handover objectives when you're giving a task to another agent. And another one of their prompt tips here is to scale effort to query complexity. So again, this is very research related. Agents are really not that good at figuring out how hard a challenge is, how much effort and how much people technically or sub-agents should they put towards this task, right? So, a simple fact might require just one agent, or, something more complex might require, 10 sub-agents with clearly divided responsibility. By the way, another useful thing to do in this situation is to keep a human in the loop. So essentially, if you're doing some sort of task that requires some sort of effort estimation, it might be a good idea to bring in a human and say, hey, does this look right in terms of assigning effort to where it needs to go? And the human can either provide feedback and say, actually, no, this task only requires this much people, and you're doing too much. So keeping a human in the loop is another sort of easy way, if that is available, to sort of figure out the effort needed. All right, so I'm going to skip through a few of these very quickly, but basically tool design and selection are critical. So you need to test the tools that you're using to solve your task. They give the example here that if the agent is searching the web for context that's only existing in Slack or like some sort of document, then that whole research process is doomed from the start. So pick your use case correctly, give the agent the tools that they actually need to use for that specific problem that they're going to be solving, right? So if your users are going to be asking questions that have things to do with some proprietary database, well, you better have a tool to somehow access that information. And then this point here sort of shows the importance of using reasoning models for some of these orchestration tasks. So reasoning models are obviously more expensive than your regular chat completion models. And so you need to use them sort of wisely, especially if you're constrained to a certain budget. So what Anthropic are essentially suggesting here is that your lead orchestrator agent that is essentially handing over tasks and sort of evaluating what things are being done should probably be some sort of reasoning model. So there's a whole separate section here on evaluation of agents, but that is sort of out of the scope of this video. So I will make a separate one on that, but I will leave the link again to the article below if you guys want to check that out. So let's talk a little bit about production reliability and sort of the engineering challenges of orchestrating these systems and what Anthropic found. Minor changes cascade into large behavioral changes, which makes it remarkably difficult to write code for complex agents that must maintain state in a long running process. So basically, agents are very stateful. They need to know what's going on at each individual step and persist that information to go to the next step, right? So you basically need to be able to execute the code, but also handle errors along the way. Because imagine you have a researcher that has a sub-agent spawned, and that sub-agent tries to call a web search tool, and that just gives them a 404 error. For whatever reason, this agent can't access the internet. Well, how does this whole system handle that? Because if the orchestrator is essentially waiting for the input from this sub-agent to come back, and it doesn't come back, then will the system fail? Or will it be able to sort of handle that error? Other thing to consider is that restarts are expensive. And so you can't just have something where, if this runs into a 404, the whole research process just starts over, or your whole agentic system starts over, because that would be token heavy and that would just be a waste of time as well. So you need to be building systems that resume from where the agent stopped, and essentially use the model's intelligence to handle errors gracefully. Again, this is also part of the prompting technique that you can use to essentially say, if this tool runs into this error, handle it this way, or if this error happens 3 times, then go back and just say you ran into an error. And so that also comes along with how well you prompt the model. Here they talk about basically having full production tracing to figure out why agents failed. So instead of just seeing, okay, this request was not very good or this request did not complete, they basically trace every single thing and every single decision sort of that the agent makes, because that data is what actually tells them which part of the agent is sort of going wrong. So in the research context, they're basically trying to figure out, okay, did the agent, for example, use bad search queries, or was it, selecting poor sources, or was it running into 404 errors while searching the web? What was the actual cause of the research to be going down, or in a more broader sense, the cause of the task failing? And so tracing and tracking all of these things and defining your own custom metrics for your use case is essentially how you can improve these agentic systems, because really you have no idea what these things are going to do, and the only thing that's going to tell you that is data. So it's important to collect data, privacy and everything in mind. So one of the final points here is that basically this whole system runs synchronously, where the lead agent is waiting for a set of agents to sub-agents to complete the tasks. And the reason that they basically are doing this is because of the simplicity of the orchestration of the process. And what you'll notice is that you can sort of scale everything parallelly and have everything run asynchronously, but this adds a challenge of coordination, state consistency, and error propagation. Because you can imagine that if you just spawn, 50 agents and each one of them does their own thing, and then 10 of them fail, and then 5 of them succeed, how can you track that state? Where does it go wrong? At what point does the lead orchestrator learn about that? All these questions arise. And so they've kept it synchronous for now, but obviously, with additional parallelism comes with all those different problems that we talked about. So usually what you'll find out is that when you do a task and you have a plan, it's good to go in small steps and have the agent execute exactly like they said, synchronously, to avoid these sort of issues. And to drive that point home, the compound nature of errors in agentic systems means that minor issues for traditional software can derail agents entirely. One step failing can cause agents to explore entirely different trajectories, leading to unpredictable outcomes. And basically, this is why the gap between production and prototyping is often wider than anticipated when it comes to these sort of systems. However, these systems have obviously proven extreme amount of value for open-ended tasks. In this scenario, they're describing research, but sort of any sort of open-ended thinking style problems where you have many paths, these systems are very useful if you prompt them the correct way and if you set up your orchestration the right way. So these things can operate reliably at scale with careful engineering, testing, detail-oriented prompt and tool design, and robust internal operational practices. These systems are complex, but basically they allow you to scale complexity across the use cases that you're solving much faster, as opposed to a single agent, and definitely as opposed to a simple hard-coded workflow. So yeah, I hope you guys found this video useful. I will leave the link to the Anthropic article down below. And again, if you enjoyed this video, feel free to check out some of my other ones. I will start posting a little bit more regularly with some more AI content. Thanks so much for watching, and I'll see you guys in the next one.